So this was our aim, I think, when we began on Monday. And while understanding the basic phenomena, as I kept stressing, we shouldn't lose sight of what the experiments and observations tell us. And at the 0th level, try to build some sort of understanding which will also rationalize or explain those, if not explain, but certainly rationalize those observations. And to do that, the first thing that we wanted to do, which was in lecture 1, was to sort of first write down, at the end of the day, it's the standard question that all of us have been sort of asked and been answering since sort of middle to high school, that if you throw something at point x at time t, where does it land? The analog of that question that one has to sort of reformulate for a flow is we wanted to understand what is u x comma t, and while doing that we saw this is all nicely classical. While doing that we sort of encountered with a little bit of phenomenology in trying to write down the constitutive relations in terms of transport coefficient, the coefficient of viscosity. We were able to sort of write down the Navier-Stokes equations. We dealt solely with things which are incompressible. All right. And we found that this was a nice looking nonlinear partial differential equation, and we discussed a little bit about all the sort of complexities which arise when you deal with nonlinear partial differential equations driven dissipative systems. And we sort of convinced ourselves the following, or maybe we didn't convince ourselves, but we sort of assumed the following, that for this Navier-Stokes equation that we wrote down, sorry, I'm using R leads to what we have here. And then in the first lecture, as should be, as a logical way to proceed, we tried to treat the Navier-Stokes equation using things that we understand from different areas of physics that all of us sort of come from, but broadly statistical physics, I would assume, was to look at things, look at the symmetries, look at global conservation laws, etc. One of the main outcomes of this on Monday was this rather surprising thing that in principle, the scaling exponent that the Navier-Stokes in the limit of vanishing viscosity or the Euler equation admits is not going to be a unique number, but it could be a number which could be basically anything. At that stage, we couldn't tell what that anything could be, all right? And then we also sort of realized that the role of nonlinearity leads essentially to two interesting outcomes. There are more, of course, but the two interesting outcomes was that it led to some sort of redistribution of kinetic energy across scales, or essentially the notion of a flux, the fact that kinetic energy at very large scales, the nonlinearity seems to sort of tell you that we'll transfer it from scale to scale. The other outcome of all of this was we looked at some simpler models in terms of bunches of ODs, etc., where we learned that nonlinearity also makes things chaotic. So this sort of gave us the first clues that there is that probably the solutions of Navier-Stokes equation and turbulence itself might have some very interesting properties which are born out of this nonlinearity. First, the fact that it allows me to redistribute kinetic energy across scales, the notion of flux, and second, in principle, this can lead to chaotic behavior. In the second lecture, what we did was we took this very seriously, and we began by saying, all right, we understand, we have our sort of tools to understand turbulence, but what is it that we need to understand, right? We have an equation which in principle, if someone solved for us, it would tell me exactly what the velocity here is at whatever arbitrary time that you want. But as we discussed, I mean, that's hard to do because I can't analytically solve the Navier-Stokes equation. I can't do much with it. So what we wanted to sort of then go back and sort of try and understand what is the phenomena that we want to solve. And for that, we took inspiration from experiments or observations or data. And what we came up with was this idea that S2 of R goes as R to the power 2/3, which is intimately tied with the fact that K minus 5/3 is the spectral scaling, and the fact that epsilon not equal to 0 in the limit of, let's say, mu to 0. And so the idea was that whatever theory or tools that we develop should at a minimum satisfy these ideas. And to sort of rationalize these ideas, we sort of looked at both cascade models, where we developed this phenomenological idea that you have large energy containing eddies, which then sort of slowly disintegrate and sort of transfer stuff from larger to smaller scales. And if this process is nice and well behaved, etc., then we certainly recover this result. All right. And here we got introduced to the idea in some formal way of what scale invariance as well as locality. This sort of led us to the sort of really seminal foundational work of Kolmogorov in 1941, 3 papers of Kolmogorov in 1941, which eventually gave us the exponent zeta p as p by 3, and independently and I always stressed on the fact that the p by 3 scaling might be spurious or might lend itself to correction, but the zeta, the third order exponent being 1 is something which has been which would be sacrosanct. And then we realized once we went through this that there are more experimental truths. So the second layer of experimental truths told us that, hey, zeta p is actually not equal to p by 3. So these ideas need to be corrected. All right? And this we sort of ascribed and we use certain words. We call this the fact that it's not scaling linearly as we had here with multiscaling, and we sort of attributed that to the idea of intermittency. And we sort of looked at little models of intermittency to see that really you could have this on-off characteristic of signals, and you can sort of play around with all of that. We then made a further digression, which is possibly in lecture 3. We made a further digression and we said that, okay, I will start to tamper with this sort of phenomenological model as we go along to try and recover these sort of experimental truths, as it were. But before that, why not actually look at some nonlinear partial differential equation which smells like Navier-Stokes, which walks like Navier-Stokes, but it isn't Navier-Stokes, which was the one-dimensional Burger's equation. Anyway, today at the end of the lecture, I will go through each of these topics, some references, so that, and I will pause like all celebrities and wait like this, so you can take a picture of each of those slides of references. I mean, there are too many, but I've divided into topics so that it's easier. Whoever wants to learn whichever topic sort of can go through it. And what we saw that within the context of the Burger's equation, and this we were able to solve analytically, this we were able to show rigorously, that for the Burgers, indeed there is an element of multiscaling. Actually, this is really a biscaling behavior. And more importantly, we are able to show that this issue of dissipative anomaly can be shown quite easily in the Burger's equation. And we went back feeling rather weird because it sort of challenges every intuition that one might have that as friction, viscosity, etc. goes to zero, things shouldn't dissipate. So with that sort of picture at the back of our mind, we sort of, I think already here, we sort of developed this idea of the beta model. This is back to turbulence. And showed that with a rather simple, elementary, but deeply insightful. Now that someone, Sulem, Nelkin, and Frisch showed us how to do it, so then it becomes quite simple, but in a sort of very remarkable insight, we are able to massage this model that we had built into one which was slightly fluctuating, and that meant that we sort of ended up killing some members of some generation, but we did it in ways, with a certain fraction, which at the end of the day doesn't appear in the story very much. And we were able to see that just with this simple argument, we could get a zeta p, which is no longer p by 3, but still, as Sanjib was pointing out the other day, still constrains the zeta 3 equal to 1 constraint. And that is sort of intrinsically tied to the idea of fluxes carrying energy down to the small scales. But this still wasn't a very happy sort of final conclusion, as it were, because this still gave us zeta p, which will be linear in the dimension or the codimension that we described. So everything now started to depend on 3 minus here, on this factor. And that, you remember, was something where we described that this whole process of cascade eventually is accumulating on some scale, on some set of arbitrary sort of fractal dimension d, which need not be the embedding dimension 3 in this story. And then yesterday, we took this process to its sort of semi-logical conclusion. And what we did it in 2 steps. We sort of massaged the idea of the beta model to effectively make it 2 beta model, if you like. So effectively introduce the fact that there could be more than 1 dimension, each of them being pegged to different scaling exponents, h1 and h2. And if you remember, what we saw there was, again, at 3, it's exactly 1, so it's about p by 3, and then it has a difference. All right? So it does break away from the simple p by 3 picture. It does start to smell that there are two scaling exponents in this story, and then we sort of convinced ourselves that we can actually choose different D1s and D2s to cook up whatever model that we like. And for burgers, we went home very happy. That's because it was able to reproduce everything else that we had seen in burgers. And so this was the bifractal model. And then, as many of you started pointing out, and your wish was the command in the 80s for several people, and you'll see some references of that at the end of today's lecture. You can actually now take why D1, D2, why not D1, D2, D3, D4, D5, why not D as many as you want. And so we went to D as many as you want, which has a shorthand word for D as many as you want, and that expression is called the multifractal model. So there we realize that instead of summing over things, because there are many of them, we worry about integrals. And what we saw was that you can sort of calculate within this multifactor picture, zeta p as some pH+3. Take the infimum norm of this. And then we sort of looked at various geometrical realizations and tried to argue the case that knowing one sort of links you to the other because they essentially are related through a Legendre transformation. Those of you who would still be up for it today evening 4-ish or whatever, whenever the tutorial is, 4:30, Sanjib? Tutorial is 4:30, right? So those of you who are up for it, we'll have a little tutorial and any other questions that you might have, or which we might be able to answer, we'll deal with that. Okay. And then we ended the last class by saying that let us go back to the Navier-Stokes equation. And we wanted to go back to the Navier-Stokes equation by looking at a coarse-grained version of it, and we introduced certain filters, etc. So today, what we will do for the next hour or so is go back to Navier-Stokes. And now, typically, there are people who like to go back to real space Navier-Stokes. Typically, there are people who like to go back to Fourier space Navier-Stokes. I have good news for you. We'll try to do both. All right. So good luck with your lunch. All right. So, okay, yeah, where we are as of Friday morning. So let's start where we left off. Okay. So remember we had defined this filter. I probably used R for this. Let me not. And this allowed us to define a space resolved up to spatial scale L, starting from the bottom, a space resolved velocity field, V of L, which just allowed us, like you take an eraser and erase around the region X. And we also saw that, just to revise, that if we define this, which is our favorite object of interest, then just a simple manipulation and the properties of phi L sort of allows us to write the corresponding high-pass filter corresponding to the same filter function as just minus. Okay, and this is all that we'll need. We'll probably need a few other things, which I will define for you as we go along, but this is effectively what we need. So with this, we can now take our Navier-Stokes equation and multiply it with the filter and essentially find the evolution equation of the coarse-grained velocity at scale L. Right? So this is exactly what I had done in the first lecture, somewhat similar in spirit, where we had looked at this filtering in Fourier space, but now we are looking at it in real space. And in the interest of time, but this is a reasonably simple exercise for you, not for me. And for good measure, let's think about C4. Okay. Now, of course, this equation can't be right. Right? This, yes. Where? Here? Yeah, so this is acting on v of r, so I'm looking at what the velocity is at x over a small separation r. Okay. Which one? Oh, sorry. Sorry. You mean this? Yeah. Thanks. Yeah. I then used it here, of course. Okay. All right. So if I look at this equation, I see the effect of the filter, which was just to hit everything, eventually gives me the same Navier-Stokes, but with little L's hanging around. But this equation can't be correct, right? Because at the end of the day, I've coarse-grained things out. I have sort of removed things beyond the scale L, so that effect must come in. And that effect comes in, and that's why I have the gap here in the equation the way I wrote it. That effect will essentially come in through the divergence of some stress tensor. So this, for those of you, I know certainly one of you with whom I was talking, who's from an engineering aerospace background, this is what you'll recognize as the Reynolds stress or the turbulence stress tensor, right? So the fact that I've sort of taken the Navier-Stokes equation and coarse-grained it has bought me one additional factor, which is divergence of a certain stress tensor. And this stress tensor, just formally, I can just write it as some VV the VV correlator L minus correlator of VL. Right? So this is just painful algebra, which is not entirely inspiring, but this is what you get. All right. So the point is, how far can we go using this sort of prescription to prove what we were proving with more phenomenological ideas? All right. So to do that, I need to have a little digression, and I should not erase what I write here because we will keep coming back to this. I will make a digression to introduce to you So I will write some inequalities, which you have to sort of go back and look up in books of complex analysis, or you just hope that I don't make a mistake like I did there with that x plus r. Right? And then we will use those inequalities to try and prove certain things. All right. So the way I'm going to define the norm of a function, so I can define, so the double bar, so I have a function f, the double bar defines for me what the norm is, and then I can sort of label with a little number p next to these vertical bars. All right? This is nothing but, and you will wonder why there's so much song and dance about it. This is nothing but, I used V for volume, right? This is nothing but taking the integral over the full volume of the function, take the pth power of this, and then for good measure, take the 1 over pth power of that. Right? So you can immediately think about very simple functions, and you can ask yourself, why the hell do we have to define everything in such complicated fashions? You will see that it sort of simplifies life a little bit, at least for those of us who sort of like working in this kind of thing. And from here, you can sort of, you can make various simpler interpretations. I'm not going to write down these interpretations, but just to give you an example, suppose you take p equal to 1. What do you think this will give us? We all know what the integral of a function over all the volume divided by the volume. We know it by a simple name, right? It's called an average. So will give us the mean, the average, whatever way you want to define it, p equal to 2. This, for example, I mean, you can immediately see that it's taking the square of something integrated over all volume, then taking the square root. If you translate that into English, it's what will be called the square root of the mean of the square, which is more simply written as RMS or root mean square. All right. Of course, you've assumed that the mean is 0 when you do this. All right. So this is how you can start thinking of norms, so that every time later when I write p's, etc., you know that at least p equal to 1, p equal to 2, you have a feeling for what these things are. Of course, various things that you can construct various inequalities. For example, you can always figure out that this will always be less than equal to that as long as p is greater than p, etc., etc. All right. So these are things that you can just play with and sort of get a handle on it. Then there are these sort of awful things where you can take p going to infinity all the way, and those are known as infimum norms, and all of them have very sort of important and interesting properties in areas of functional analysis and all of that. So the other properties that we deal with, so maybe I'll remove this so that I want to keep this, but I don't want to occupy the whole board while keeping this. And I'll keep on adding more properties. So the other properties that you can think of for some norm that I'm not even going to define, I've defined the FP norm in the following fashion, but I can certainly define other norms, and I can think, and I can say that the properties of them will be something like this. If I multiply something with a scalar, then this will be nothing but whatever the scalar is, the norm where I can think of the analog of the triangle inequality, and I can etc., etc. So we'll fill the board up with some of these things, and we'll try and see why they might make sense. This has some more. I can actually write the integral version of this, so many of you might know this. Those who are, so I can take an integral, let's say, for the pth norm. I can always show that this etc., etc. All right. The norm of the integral is bounded from above by the integral of the norm. So what we will do is, while you're sort of telling yourself, thank God this is the last lecture, what we'll do is we will try to exploit some of these properties in a simple way and show that they lead to the kind of experimental observations that we are after. So remember, the first sort of experimental observation that we are after was the idea of anomalous dissipation. So let's see how we can use these ideas to actually come up with. So in the sort of coarse-grained equation that we have a viscous term, and the viscous term is nothing but the Laplacian of phi of L at x. Now we know how to write this. We know how to write this. That's because we will pick up nu, then we can, the definition of our filter allows us to commute space derivatives and the filter. So I can take the Laplacian inside, and what we'll have is some grad squared over phi L. This is picked at R, and then in our usual definition. All right. This I'm just getting by integration by parts. Nothing more, nothing less for a divergence-free result. Because we had something which was scale dependent as 1 over L, remember when we set the scale L to the projected the previous day, we picked up a factor of L. So now I'll need 2 factors of L because of the Laplacian. I'll just write it as nu over L squared. So what you can do is you can immediately see that if I want to write the norm of this guy, the norm of the pth norm, and that is going to be related to this integral quite trivially, you see I can make use of this sort of argument. Right? We didn't prove where these sort of results come from. We'll just use these arguments. Right? So just using this in one step, I can show that this will be nu over L squared, some constant coming from here, which I really don't care about. Exactly the same result that we had here, right? Except I've performed the integral and scooped out a constant, which I really don't care about, right? Now this is very interesting. What's interesting is this is my dissipative term, right? Because at the end of the day, the norm here tells me that I've actually integrated that animal over the whole domain, and so it's essentially epsilon that I'm looking at, right? But this is kind of perplexing. This is kind of perplexing because I can take the limit of nu going to 0 here, and if my v, the pth norm of v, which I'll just calculate by replacing f with v out here, if this remains finite, then this animal certainly will go to 0 as viscosity goes to 0, right? For this doesn't help my cause, right? Because, oh, I've erased everything. Because we are after trying to look at experimental facts of this actually not, hopefully the dissipation of not going to 0. So this, of course, has a trivial consequence that you can check for yourself, because you take this equation, integrate everything out, take the L limit, and what you will see that in the absence of any forcing, etc., you will always have d dt always being less than 0, because this comes with a minus sign. Right? Very good. So this is no good, but now, because we've coarse-grained things, we have an additional term that might save the day for us. And that additional term comes from the additional stress tensor that we have, right? So what we can try to think about is try to massage this divergence of this stress tensor in exactly a similar fashion and try and see if we get more out of this game. Because at this stage, we don't have much to go about. Okay, very good. So let's write this in terms of energies. So what I want to write is I want to multiply everything with VL. So I can write down the effective kinetic energy at length scale L. And I'm going to see what is pumping in energy at that length scale L, what is dissipating, and whether there is a constitutive relation in all of that. Okay. So what we'll do is, if we define some energy density as half and some total energy which will be defined as some stylized E, L, and T. What we will have from the Navier-Stokes equation is, well, from that equation will be there'll be a terrible term sitting here. Tensor product we've already seen that the integral of this will go to 0 at small l. This term essentially will contribute what's known as the energy flux. And this term, we will write it as some sort of a pi L, right? So I'm skipping some of these steps simply because of lack of time, but okay, so I should tell you that the idea of this exercise is not for you to be able to do it immediately, all of this. I'll give the reference where you can go through this step by step. I'll also scan the notes and put it up on the website. But the idea for this is to show you one way to think about this problem. All right. And so what we are after essentially is to estimate the energy flux that's going on in this system. So what we will see at the end of the day is that the flux will be defined as this. You will just get from the way I had defined my TL here, right? I've now multiplied by V, so that's what I will end up getting. And one can sort of use exactly similar arguments as we have done before. And the idea is, if I want to know what is it that my flux depends on, I need to be able to compute separately what is the order of the stress tensor and what is the order of grad VL. So let's look at the grad VL. The stress tensor, I will probably just write down the result. So if I think about the grad VL, then I will use the same definition that we wrote on the first panel of the blackboard. And what we will have essentially is ddr grad phi L Vx plus R. But remember, I can trivially add a V of x there because that does nothing to the integral. And so, because of the gradient, I pull out a factor of L in front. I will essentially have as before, this part will give me a constant, which I really don't care about. And so this thing will end up being some order in delta V. L is the scale at which I'm co-screening divided by. At least dimensionally it's consistent. So if you don't want to worry too much about filtering, think about the gradient of a function being the difference of the function divided by the scale at which you calculate the difference. Right? And using absolutely similar tricks, you can also show that tau L x will be equal to delta V squared. Okay. So what we end up from there is something that doesn't surprise us, some constant, which I don't care a lot. When you see this, you realize this is exactly the same result we had in the phenomenological model. Remember, we were getting V cube over R all the time, except now I get it in terms of bounds. So I say that the largest flux at point X that I can think of is bounded from above with some order 1 constant, but delta V cube over L. So this at least sort of corresponds to things that we've already seen. So now what this tells us is that, for example, if V is differentiable, then I can write down my delta V simply as you want to do this more formally, what you have to do is take the supremum of all the V of x in the vectorial sense, and you'll see there's a 1 over L sitting outside. That will give a number, so I really don't care. I'm after the L dependence. And so this, in a sense, will give me order L squared, which as L goes to 0, goes to 0. So if only this is the physics that's going on, I will never be able to recover the Onsager result or the dissipative anomaly effect, which is what I'm after, to show systematically that there is, that if certain conditions are met, then epsilon will not go to 0 in the limit of viscosity going to 0. Right? So far, what we've done in the earlier case, which was here but erased, or in this case, what we've assumed is that if V is sufficiently continuously differentiable, you end up with a flux which is order L squared. In the Reynolds number going to infinity limit, L will go to 0, and so the flux itself will go to 0, and so you will not have dissipative anomaly, which is one of the experimental truths that we have to contend with. All right. So let's try to understand how we can cure this. How is it that I can replace this L squared with something else such that it will not go to 0 anymore? Right? So that's what we'll try to do. So what we'll first say is what happens if I'll explain what this means. So around point x, we will assume that v of x is Hölder continuous with an exponent h. What that really means is that if I calculate delta v around point x over a distance r, then this is bounded by as long as, let's say, r is within some radius r0. Right? So I'm standing here and I'm saying that if I take little differences between points r away, as long as r is not too far away, too far is defined by r0, then the difference of the velocity field will be bounded by the separation to the power h, where h is some Hölder exponent, and h. Right. So if this is true, then delta V should be of the order L over H. Right? Well, I want to look at it over a scale L. That scale I'm still assuming to be within R0, so my velocity separation will be L to the power H. Right? You can sort of quickly see for yourself here that, to cut a long story short, that if I write this as L to the power 3h minus 1, 3h coming from this factor, 1 coming from here, then certainly for h greater than 1/3, this will always go to 0 as L goes to 0. Because if h is greater than 1/3, and 1/3, remember, is the Kolmogorov exponent. If h is greater than 1/3, then a small number to the power something positive will go to 0 reasonably quickly. All right. So is there a way we can think about h being less than 1/3 within this formalism? Right? And we've already seen, right? Remember the experimental result of zeta p versus p? They were all curving away from the p by 3 line. So it's possible that you will have some range of h's somewhere which are less than 1/3, and so everything will be fixed for us. All right. So how to make this idea somewhat more concrete? One way to make this idea somewhat more concrete is if I look at the total flux. So I'm not going to look at the flux point by point. I'm going to sample over all space. So essentially what I'm after is some sort of volume integral of pi L. And now you can use your favorite sort of ideas of norms, etc., and calculate everything that you want from this integral of pi L of x. Right? So what you're able to do is the following. Well, you can go through a little bit. What you're able to show is if I calculate the norm here of some 1, this will always be was one of the conditions that we had written there. Right. Now this is more generalized, so maybe I write it here. So I write the Hölder inequalities. That's the general Hölder inequality. So if you take the product of two functions, take the first norm, so integrate and get the mean of those products, then they will always be less than equal to if you did it for the individual cases. And in general, you can do it for any number of these guys. So in general, you can have the product where I goes from 1 to n of as many functions as you like, and this will always be what it's what it says is if you have a product of, let's say, 3 functions, f1, f2, f3, multiply those 3 functions, take the rth power of the multiplication, integrate it, then take the 1 over rth root, the number you will get will always be less than if you did that operation for those individual functions and multiplied it all together. All right? Now, the reason we need this is, as we had seen, the flux was determined by 2 functions, right? There was the grad VL, which was acting on the tensor tau L. So I can use this, in fact, to now calculate what that flux will be bounded by. All right, so let me work that out explicitly. So what we had was the following. What we had was pi of L right. So this inequality would mean that if I were to take pi of L to the power, the rth norm, then this will be bounded by grad VL 3R. That's because 1 over 3R plus 2 over 3R will satisfy 1 over R, right? The constraint that we had there. So in order to make life simple, I can take P to be 3R, let's say, for the rest of the calculation, and which means R will be P by 3, and P will be But we already calculated explicit representations of this. This came, if you remember, with a 1 over L factor sitting outside on on VL, and this came because of the Reynolds stress contribution, which was the VV mean minus V mean tensor, right? So you can actually calculate this, and we can show the following. So I'll just give you the result. I won't go through the analysis at all. What you can show is, so we need first to calculate grad VL, where 3R is equal to P, as we discussed, and we can show that this is some constant, some number we can show tau L. So then if I use this inequality, then I will have the Lth norm P to be order. Let's just interpret this result, and I think we can close this idea just to say what this is telling us and how it connects to the picture we had of zeta P going like this, where P equal to 3 is here, and the fact that your dissipation rate as a function of 1 over nu goes to a constant. So what is it telling us? It's telling us that for P greater than equal to 3, which is somewhere here, beyond this curve, if L goes to 0, this thing will go to 0 only and only if sigma P is greater than 1/3. So it's giving us a somewhat negative result. It's telling us that the flux in turbulence, if I derive it from the coarse grain description of the Navier-Stokes, I will necessarily end up with a flux whose pth norm for P greater than 3, because that's the only bound that I can make, necessarily vanishes if the Hölder exponent sigma P is greater than 1/3 for P greater than 3. Right. So what it's saying is that if you were to get exponents, let's say if your 4th order exponent happened to be 4/3 or larger, then you can never get anomalous dissipation. It's telling you that your any order exponent greater than 3 has to be less than P by 3 for you to get anomalous dissipation. So in a way, this sort of approach, I've sort of just sketched it out for you. I know it's been not hard to follow, it's been impossible to follow, let's put it that way. But this is just so you'll have it in my notes, the steps in the calculation. But what we are trying to say that really using norms which have nothing to do with turbulence as such, which have everything to do only with ideas in random functions, all of this is true. It doesn't really matter whether you're looking at a turbulent field or some other function space. All that it's telling you is if you sort of painfully calculate those integrals and take pth powers and then take 1 over p powers of certain integrals, then you will always end up with this sort of a result, which tells you very convincingly that the only way these two pictures can be reconciled and they form part of the same experimental data that you're looking at, the only way that can happen is if zeta p for p greater than 3 is less than p by 3. For pi and hence epsilon to be not equal to 0 as nu goes to. So this is in some ways a very strong result, because this sort of gives a much firmer mathematical footing, beginning with the Navier-Stokes equation, which tells you why multiscaling is a necessary evil in dealing with this sort of problem. Yes. Which one to be held to continuous? Yes. That is an assumption. What we are not assuming is how continuous is continuous. So what we've assumed here, absolutely correct, I should stress it a little more. What we've assumed here is that this guy is the difference, what we've assumed is that delta V is bounded by some L to the power sigma P or L to the power H, whichever way you want to think about it, where this could be anywhere between 0 and 1. If I push it all, so, and then what we find is that 1/3 is a somewhat critical point in this picture. So in about 15, 20 minutes ago, we looked at just a trivial example where H would be 1. So that would be in the class of continuously differentiable function, Taylor expansion, in other words. There we saw that the flux goes to 0, right? So then we said, all right, experiments suggest that the dissipation rate is not going to 0, so we should try to think about delta V not being proportional to L, but let's say proportional to some Hölder exponent that I don't know, except that it's between 0 and 1. And then we find a constraint on what that scaling exponent can be for anomalous dissipation, which is an experimental observation, to happen. This gives us a bound. So now, how sharp you can make this bound? I think you cannot make, 1/3 is really the sharp upper bound. The lower bound, you really don't care. Yesterday we saw from a different picture that H min is always positive. That's about all that one can say. But from here, all that you're saying is, suppose your experiments, you did an experiment. Now let's see what this is saying. So if you did an experiment and you found epsilon versus 1 over nu to be a constant as nu becomes large, and you also measured the scaling exponents, let's say, 4th order, and you found a number, let's say 1.48, right? This result will say that there's a contradiction. If you found the 4th order exponent to be 1.48, then you cannot find this. So that's the power of these sort of calculations. If you found your 4th order exponent to be 0.87, then this is fine. Except we are still in trouble. That's because we know this would be 1. So the 4th cannot be smaller than the 1. So you better find zeta 4 to lie between and that's all this result is telling me. All right. Similarly, it will tell me for zeta 5, I'll just replace this with 5, etc., etc. So it sort of provides me a lower bound as to what the scaling exponents could be to rationalize the observation of dissipative anomaly. But it's not giving me a sharp number. So it's still not giving me y zeta 4, the sort of measured value, let's say it's 1.27 or whatever that number is, 1.24 maybe, I don't remember. It's not going to give me that number. But it's going to tell me if you found it to be 1.37, then something is wrong in your experiments or in your measurements or data analysis. Maybe you calculated the fifth order, but you thought you were calculating the fourth order. So this really tells us exactly the limits of where we can be. Okay. So this was sort of, shrunk about in a couple of hours lectures into half an hour or whatever, but just to give you a feeling for those of you who are interested in more mathematical approaches, that if you, up to here this is fine, but if you begin with such an approach and then you have a book on real analysis next to you where you can look up these results, they're not hard to prove, most of them, then you're able to say a lot more about what's going on in a slightly more formal manner. It will be in terms of bounds, as she was pointing out, and not in terms of actual numbers, but that's better than nothing. Okay. All right. So we have about 20 minutes left. So do you want to go through similar analysis in Fourier space, or you guys are very tired? Or I can give a general overview and finish. Huh? You want me to go through the Fourier analysis? You don't want to be the unpopular guy in the room? Huh? You want me to go through the Fourier? Oh, very good. No one's contradicting him, so you suffer. I mean, me as well, but. You're just hoping that it will be better than what went before, and so you might go to lunch feeling happier. That's a good attitude to have. Hope is always a good thing. Don't worry, at the end of this, I'll give the reference where you will see all this worked out in full detail. I'll also scan my notes and send it over. Okay. Fourier. So where is Fourier? Fourier is here. We've talked a lot about R2/3 and P/3. Let's now talk about the analog of that result, which is in reality the exponent that you measure. So this is Kolmogov's law, which comes from the fact that second order goes as 2/3, etc., etc. In reality, we didn't look at that, but in reality, even within the beta model, the bifractal model, all of that, you saw we had a correction to the scaling exponent. So there's obviously a correction to this minus 5/3 because it's just related trivially as a Fourier transform of each other, right? So what we will try to see is there a completely independent way to arrive at this k minus 5/3 result. It's not exactly what you will see in experiments, because in experiments you don't see 1.66666666667. What you in experiments what you will see is maybe minus 1.71, and that small difference comes from all the things that we've discussed over the 3 lectures, that p by 3 is not exactly correct. All right. So the Navier-Stokes, just to sort of set some notations. So formally, maybe I can begin. You did have some Fourier transforms of the Navier-Stokes in the tutorial. Okay. All of you know Fourier transforms, right? So essentially what we will deal with is, where is chalk? We will be in the space of periodic functions that you're not allergic to. Right? And vice versa. Similarly, the pressure field will also transform into its Fourier component. So formally, what we can do right is the following. Some nonlinearity u hat, which comes from the convolution of the u dot grad u term and the pressure term, right? Because the pressure term you can always write in term, if you take the Fourier transform, you can write the pressure term as some sort of a Fourier transform of what you had in the nonlinear term, right? So this you do just by taking divergences, which I haven't. So I should have a minus k squared pk out there, all right? But formally, I can always write the equation of motion in terms of a nonlinear term, which depends on Fourier coefficients u hat. I'm not putting the labels, and you have the linear term here. And so in general, I can sort of always write this, because that's a nice way to think about it, in terms of some 2-vector component, some other label. So I write it for the Fourier mode k, and I write it for the Fourier mode k prime. I write exactly analogous equations, and this is a standard trick that all of us do because we now want to build up tensors. And then I can multiply this guy with u of k prime and this guy with u of k, so I get the product exactly the same. And so when the dust settles, I can write this as we will be slightly more precise about the angular brackets later, but let's assume it's an ensemble average over different realizations of initial conditions. All right? So all I've done is written the Navier-Stokes equation for 2 different wave vectors, k and k prime. Then I've multiplied the upper and the lower equation with the corresponding ones, and I've added all of them up. So the question is, what is this animal going to tell us? And how is, of course, it's quadratic in u hat, so you can see that it might lead to something in the energy spectrum that we are after, but how do we go from there to the energy spectrum? So what we can do is the following. Well, skip some steps, but let me know if you're lost. So let's define position vectors x1 as x, and position vector x2 as x plus. You may have seen part of this in the derivation of the energy spectrum from the second order structure function, right? So maybe I can just sort of skip the intermediate steps and essentially define my velocity correlation tensor, which is at point x1, x2, t1, t2 as nothing but ui. That's my capital U. So what you have seen in the tutorial, and even if you haven't, that's a simple sort of Fourier transform property. What you will see is that ui k t1 uj. This is the correlation that you would have seen in the tutorial. Right. So when you play this game, let me make the following remarks. Hermitian spelling, E-T-A-N. Okay, if you make, I was a bit lost by the Hermitian, there's another E somewhere. If you make, take recourse to Hermitian symmetry, then what you will end up getting is you don't worry about the vectors anymore. So you see, we have some corresponding terms sitting here. So I can replace this by what I got here. Take delta k plus k prime. Then, if that's the case, then I make use of this following identity. And then I can relate all of this in the following simple fashion. Let's say I want to calculate kinetic energy. Kinetic energy will be in real space which from the definition of the tensor that I had there will be nothing but all I've done is I've just sort of exploited basic ideas of Fourier transform, right? Now this decay in this you must have done, right? So this decay in 3D space, I can write this as some 4 pi k squared dk, the d vector. And so I can calculate the total energy as, well, let me keep half. By definition of the energy spectrum, which should be k minus 5/3, I can identify this as some Ek Along the way, I've lost track of some of the 2 pi's, etc., but that's not super relevant to what we are going to do. Right. So now you already see something nice which is going to emerge. What you see is I can actually reduce this problem by using first the delta correlation. So that would mean that I can replace this by just 2 new k squared, because k and k prime are going to be same. And then I can stick this k squared over here, which is the tensorial product that I have. And I can write essentially things in terms of the energy spectrum, which is what we are after. Right? So that's the formal way to do it. All right. Of course, I'm still stuck with the triple correlator, but this is the standard closure problem that I have, and I need to calculate this triple correlator from the next order term in order to get some work done. All right. So is the rough idea clear? So the rough idea will tell me that I have now del t plus 2 mu k squared k. I've taken further factors of k squared. And so this will be some transfer term, which I do not know, which is a sort of shorthand way to write these triple correlators, right? And I'll try to sort of make life simple for us. And the triple correlator, just for completeness, will be something which is going to be proportional to, let's say, k squared, some s, which involves these sort of 3 wave vector interactions. Right? These 3 wave vector interactions have symmetries, etc., which which comes in very useful. But I'm just going to just formally set up this problem to see how this can work out. Right. And so within this sort of context of the transfer term, what we can do is we can also write the flux, the same flux, but now in Fourier space, which is the transfer which happens from wave, the flux at wave number k is going to be the transfer that takes place from wave number k all the way to infinity. Right? If that transfer turns out to be positive, it means it's sort of flushing things from k to infinity. If it turns out negative, it seems that it's sucking out things from infinity to k. All right. So what do we get from here? What we get from here is the following. So what we have is transfer and some forcing F0, right? Let F0, because we, to have stationary solutions, I need some forcing to inject energy, which is getting lost by viscosity, right? So let's assume that my force term acts somehow around some wave number ki. Right? So now I can calculate the integral of this guy. I can calculate this integral in many different ways. One way I can calculate this integral, because you see that will end up getting my flux term out of from the system, is the following. I can First, what I can do is, so F0 equal to F0 for K not equal to Ki. Right. So in steady state, what I have is the following. So if you have steady state, because I've added the force and there's dissipation, so essentially the equation that I'm looking at is now I can integrate this equation, right? So for example, epsilon will be the integral from 0 to infinity of 2 nu k squared. Right, that's the total energy that's going to be dissipated. So and the power that's going to be injected will essentially be right. So with this definition of the flux, what you can go back and check clearly is the following, that this balance has to be followed, right? Is this clear, or do you want me to go through this a little? Want me to go through this a little? So you can do it in two different ways. One is I can do the following, which is the easiest and the simplest way. I can, let's say, integrate this from 0 to Ki, all these terms. And then I'm going to see what the cancellations are, because my flux is defined as K to infinity, which is the same as saying minus infinity to K, T of K, and then you can evaluate these integrals yourself and see that indeed pi of K is equal to P is equal to epsilon, something that we've used quite a bit in the class. Right. So far what we've done in Fourier space seems to be fairly consistent with the phenomenology that we developed in real space. So this was just a way to show you that that consistency holds, and the fact that this sort of description tells me that the injected power is the same as the flux is the same as epsilon. Okay. So if you, just to finish, so for example, if you take the limit of the integral 0 to infinity, you get an epsilon here. You get nothing here because of the reasons we discussed there. This integral 0 to infinity vanishes because transfers conserve, and this will just pick up the injected power over all wave numbers. So 0 to infinity will give you P equal to epsilon. Now if you do from Ki to infinity, then this term doesn't contribute. You will see this is equal to epsilon, and hence you get the final result. All right. So back to the equation. So what we have is del T plus 2 nu k squared Uij equal to a triple correlator. And similarly, if I go to the next order, and so on. Now we know we can sort of make a first approximation, approximation 1. And this you did in the last week, which is I can assume U to be Gaussian to a first approximation, which would mean that I can write the 4-point correlator as the sum of products of 2-point correlators. So I can replace this as the sum of this is strictly true when things are Gaussian, so this is a approximation that we are going to use. If we use that, then what we can certainly say is the following. That's because I really need a formal expression for this triple correlator, which I'm going to put in there. That's the whole thing that I'm after. So when you do that, now I'll just sort of wave my hands a little bit. You can see that this is an equation of the following form: ddt plus something multiply the function that I want to evaluate. So you know how you can formally do this integral. You immediately will notice that this term will appear upstairs as exponential minus something. So when you do that, what you end up getting is the following. This term coming from the formal integral representation here. So I've taken an integrating factor exponential minus nu k squared plus q squared plus p squared. I need to evaluate this at time t because everything on the left-hand side is time t. So I'm doing an integral from 0 to t on the dummy variable tau. All right? And the fact that I have this sort of averages, that means that I'm dealing with integrals over wave numbers p and q. We do this in a special way, which we won't have time to go through. But essentially, when the dust settles, what you have is a reasonably simple form. Don't worry about the form, but something which looks like this. So that's a horrible looking form. And that comes from the fact that, your fault. That comes from the fact that we have formally integrated the triple correlator by expanding the 4-point correlator as cumulants. Right? That's all we've done. So the rest of it I will not do at all because it's quite late. So the rest of it involves the following 2 approximations. I will just tell you what those approximations are. Those of you who are interested, stay back. The others run for lunch. So the next approximation that we need to do is something that all of you know, is that I have written the 4-point correlator as the sum of products of 2-point correlator. But we know from everything that turbulent fields are not Gaussian. I mean, this was all that we studied in the last 3 days, right? So there must be a non-vanishing cumulant in this game. So that non-vanishing cumulant, this was, I'll show you the references, great work of Ozak and others, who sort of approximated this non-vanishing cumulant as some sort of an additional frictional term, all right, which can be, which sets a certain time scale in the problem, all right. So what you can do is you can cure for a non-vanishing cumulant by sticking in an additional time scale in this problem, an additional drag, if you like, in this problem. And then the last thing that you want to do is what would be called formally as Markovization. Essentially, you want to get rid of this time integral, right? So you get rid of this time integral by assuming that this chap has a certain relaxation, And so I'm going to lift that time integral, and I want to get rid of it, so life is simple. And what you end up, and really this is the last equation that I'll do right for you, but I will sort of tell you why this is very useful. So what you do at the end of the day is get what is known as ED, which is for eddy damped. That came from the fact that I needed to cure for the fact that my cumulant is actually non-vanishing. Qn, that stands for quasi-normal. I began with assuming Gaussian fields, but it's really quasi-normal, and that quasi part is being cured by the eddy damping. And then I added an M, which stands for Markovization. That was to lift the time integral and make sure that that doesn't exist. And mouthful, but what you end up getting is a closed form equation which is easily solved. Integral over dp dq. These two wave numbers stick in because I had that triple correlator that I began with, so I needed dummy variables. They all integrate over a triangle of wave numbers such that p plus q plus k equal to 0. Then I have some effective time scale, which is just shorthand for writing whatever I have here with the additional drag. Then there's a whole bunch of horrible coefficients. B is a coefficient, E of Q, let's say. This multiplies by K squared, E of P T minus P squared, E of K T. Okay. This has a long, glorious history, but perhaps not as glorious a future. All right. So what you end up getting is a closed form equation of E of K over T. And what you can show, I think I won't show it actually. What you can show is that but those of you who want to see it explicitly, just stay back. It takes a few more lines, but we can do it. But what you can show is that the simple fixed point solution to this equation gives you E of K with very reasonable assumptions goes as 2/3 K minus 5/3. What it really cannot give you is any intermittency corrections. It's just a more formal way from the Navier-Stokes to prove Kolmogorov's result of K minus 5/3. But it tells you nothing about any higher order correlation functions. You're stuck with just calculating energy spectrum and chasing your tail for the rest of your life. And secondly, it really does not give us what is the most interesting thing in turbulence, which is the correction to this 5/3, albeit small. It just gives the Kolmogorov fixed point, but you see it, for any of you who are formalists, you actually like, the sort of dreary path to go through this calculation in detail, and people use it. It's not that it's not being used, but it's used. I mean, one of the advantages of this calculation, now I'll give you the references and we all have to run for lunch. One of the advantages of this calculation is it allows you to solve turbulence also in arbitrary dimensions, because dimensions enter very trivially, well, not very trivially, but enter in a nice fashion in deciding, in evaluating these coefficients. So what I'll do is, I'll just flash the two slides of references because there's a lot of, so any of you who want to see what those references are, you can take screen photographs of it. Oh, there is a telephone. Yeah, that telephone actually connects there. That's true. I'll also be at 4:30. You don't have to be here, but those of you who want to worry about today's class especially, to fill in the details, you can come at 4:30. I mean, you can also quiz me later. I'll be done in 2 minutes. Thank you. I'll just give you the list of references and I'll sort of space it out topic-wise so that you have some. Huh? Yeah, yeah. Yeah, I'll scan all of this and put it all together. So for basic fluid dynamics, there's sort of three. So the color coding is blue are textbooks, green are lecture notes or review papers, and everything else are just papers. So chaos and deterministic models, experimental results, Kolmogorov theory. There were 3 papers actually. He didn't write it in 1991, he wrote it in 1941, but that's probably slightly harder to read. It was then translated and the Royal Society came up with a transfer. I've just given that reference. Then Berger's equation, Berger's own book, the first one, which is very, very nice actually. 2 review papers. We discussed a lot about fractals and dimensions and weird objects. So a nice book is the one by Mandelbrot, sort of the father of this field, as it were. And the second part is where it gets worse and worse. So for the beta model, you'll see Uriel's book is a nice place, of course, to look at it. But then it's a sort of semi-forgotten paper of Novikov and Stewart, and then the Frisch, Suleiman, Nelkin paper, which actually, it's often very nice to read the original papers because they're very well written, and you see. The multifractal formalism has a very, very long list and application, so this is just some of the papers that I'm familiar with. It's not supposed to be exhaustive. The last paper, the one by Dhrubaditya and Rahul, is particularly interesting because you'll see how you can extend the ideas that we have in a non-trivial fashion for time-dependent. Those of you sort of worry about critical phenomena to how to think about dynamic exponents within this formalism. Then what we really did today was these 2 topics, and the book, Lissier's book is very good, but what's very nice is Steve Ozag's lecture notes on statistical theories of turbulence and the Rose and Sulem paper. But if you again want to go to the source in some sense, would be the old Crichton work from the 60s. And then what we did as a memory was, of course, to show that these ideas are applicable across different problems. Goes back to Da Vinci. But just to remind you, and this is really it, and we can all go for lunch, what we were after was that scaling peak. This is taken from Uriel's book. The Reynolds infinity. Now there's sort of different paths to go to that route. One is the renormalization group, which we didn't touch in this lecture at all, except in a loose sense what we did today, but not really. Then there is mathematics, which we didn't touch except in a loose sense in what we did today. This was just to give you all some flavor. Then phase de la fermeture, which means closures. That's what we covered, a history of 25 years of closures in about 7 minutes. So that's another path. What we really focused on was the other path of cascades, data from experiments, intermittency, and all of that. Okay. And the second book is very nice if you want to draw some inspiration about the subject, which is the historical thing. All right, so goodbye. I will see you later. Those of you who know what the siren is, I will not explain why that picture is there. Those of you who don't, you can Google the relevance of siren in mythology. Okay, thank you. So I will see you all, those of you who are still there.